Good morning to everyone. I am Dr. CHITRA Devi from CSE department. Today I am going to take minimum spanning tree. First of all, we should know what is minimum spanning tree. So first I am going to define what is minimum spanning tree. A minimum spanning tree is a fundamental concept in graph theory and computer science. It is a subset of the edges of a connected, undirected graph that connects all the vertices together without any cycles and with the minimum possible total edge weight. While doing the problem, I will explain what it is. Okay. First, you will know what is definition alone. So these are some of the key properties of minimum spanning tree. First one is connectivity. Connectivity means it is a minimum spanning tree ensures that all the vertices of the graph are connected. Second property is it should be acyclic graph. That is, there are no cycles within the minimum spanning tree. Third property is optimality. The total weight of the edge in the minimum spanning tree is minimized, making it the most efficient way to connect all. These are some of the properties of the minimum spanning tree. Next, we will see what are the applications of the minimum spanning tree. First application is network design. Second one is clustering, and third one is approximation algorithms. So these are the three applications of the minimum spanning tree. So main thing is network design. In network design, minimum spanning trees find applications in designing efficient network layouts such as laying down cable infrastructure or designing transportation routes. Okay. Second application is clustering. In data analysis and machine learning, this is mainly used clustering method. That is, minimum spanning trees are used for clustering data points into group based on proximity. Third application is approximation algorithms. That is, minimum spanning trees are utilized in approximation algorithms for solving complex optimization problem. I think everyone know what is optimization. Optimization means if it is in terms of cost means it should maximize. If in terms of route means it should be minimized. So optimization means it can be a maximized or minimized. We have to use accordingly. So these are some of the applications in minimum spanning tree. Next one is what are the algorithms we are going to use in minimum spanning tree. We are going to use two algorithms. One is Prim's algorithm, another one is Kruskal's algorithm. So we will be using both the things. That is, first one is what first we will think what is Prim's algorithm. That is, Prim's algorithm is a greedy algorithm that starts with an arbitrary vertex and grows the minimum spanning tree by adding the shortest edge that connects a vertex in the minimum spanning tree to a vertex outside of it until all the vertices are included. This is how we will be using the Prim's algorithm. Second one is Kruskal's algorithm. So in this Kruskal algorithm, this is the another grading approach. Both are greedy approach only. This is another way in greedy approach. Here in this starts with an empty graph and adds edges to it in increasing order of weight, ensuring that no cycles are formed until all vertices are connected. So here the main thing is in minimum spanning tree, all the graphs will be an undirected graph. There won't be any direction for the graphs here. Okay, so that we should keep it in mind. That is, all the graphs will be a undirected graph. So we are going to use only the undirected graph for the minimum spanning tree. So this is the complexity of the minimum spanning tree, that is order of E log V. This is the complexity. Here E denotes the number of edges, V denotes the number of vertices in the graph. This makes them efficient for large scale problems. So two things you should remember, that is E stands for edges and V stands for the vertices here. So this is the optimality, that is minimum spanning tree generated by Prince or Kruskal's algorithm is guaranteed to be optimal, meaning it has the minimum possible total weight among all spanning trees of the graph. Okay, and what is variance and extension? So various extensions and variants of the minimum spanning tree exist, such as maximum spanning tree and the minimum spanning forest, which deal with the different optimization criteria or graph types. So what is the conclusion of this minimum spanning tree is, minimum spanning tree trees are the crucial concept in graph theory and have a widespread applications in various fields due to their efficiency and optimality in connecting various vertices while minimizing the total edge weight. So here this minimum spanning tree is used in various fields like transportation and many other things. Okay, so here the main thing what we are going to do, it means you are going to minimize the total edge weight on the optimality in connecting vertices. Okay, this is what we have to remember it. That is, one thing is, in minimum spanning tree the graph will be an undirected graph and you will be having a vertices and edges you will be having, and it should not be a closed one. Okay, this is what you have to remember it. Then we are going to we are moving into the problems. That is, in each and every year you will be having at least one problem in minimum spanning tree in GATE exam. Okay, so already I have, in this presentation I have solved totally 8 problems. I have started from the 2021 problem. Okay. So here minimum spanning tree, first you should know what is minimum spanning tree in short before going into the problem, right? So here minimum cost spanning tree is actually, we are going to draw the subgraph here. That is, a subgraph of a given graph is said to be a spanning tree. Subgraph is a minimum spanning tree if and only if it satisfies all these 3 points. That is, the first one is, it should contain all the vertices of the given graph G. Okay, first point is, it should contain all the vertices of the given undirected graph G. Second one is, it should contain n-1 edges, where n is the number of vertices here. Suppose in this, if we are having 8 vertices, means number of edges will be 7 in the subgraph. Okay, and it cannot contain the cycle. The main thing is minimum spanning tree, it should not have the cycle in the subgraph. So these 3 points you should keep it in mind while solving the problem of the while finding the minimum spanning tree. Okay, first thing is, it should contain all the vertices of the given graph and it should contain n-1 edges, where n is the number of vertices. Third one is, S cannot contain the cycle. First, we will move on to the question number 1 here. So here, consider the following undirected graph with edge weights as shown. So this is actually a GATE 2021 question. That is, this question is in set 1 question paper. Okay, I'll start with this. So here, already I told you that this is, we are going to consider for minimum spanning tree undirected graph. Undirected graph means this is the undirected graph. There is no direction for this one. So here we are considering this undirected graph with edge weights. So here this is actually a vertices. Okay, how many vertices we are having? We are having totally 8 vertices. So here in this undirected graph, undirected means what? This is what the undirected graph. What do you mean by directed graph? Directed means you will be having some directions for it. This is what directed graph. So we are not going to consider this directed graph here. We are going to consider only the undirected graph here. So how many vertices we have here? How many vertices here? 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally 9 vertices we have. How many edges we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. How many edges we have? 10 edges. So here, what is the question means? Here, the number of minimum weight spanning tree of the graph is. So we are going to find how many minimum weight spanning tree for this particular undirected graph. Okay. So here we are having 9 vertices and the edge is 10 here. So what is the condition we have? You should have the formula is n minus 1. So what is the n here? I will tell you later what it is. So here we are going to find how many number of minimum weight spanning tree for this particular graph. So first thing is, what we are going to consider, minimum weight here is 0.1 is the minimum weight we are having here. So we are going to consider all these things here. So what is the thing here? Consider all the vertices here, and then minimum weight is this one, this one, this one, here, and then we have this one. We have taken all minimum weight, that is 0.1. Next, we are going to consider this 0.9. That is the condition, one condition you should remember, that is it should not close, that is the cycle should not be closed here. Okay, so here if you are considering this one, how many vertices you have? You have 9 vertices, edges are 10 here. So here, if you are considering 0.9 here, the cycle is not closed here. How many edges you have now? 1, 2, 3, 4, 5, 6, 7, 8 edges we have. And then this is one minimum weight spanning tree. Another one. Another, which one you can consider? If you are considering this one, this is one minimum weight spanning tree. Next, which one you can, this is one minimum spanning tree. Next, which one you can consider? Suppose if you are considering this weight, now we cannot consider this one. Why this so means? Here the cycle is closed. So you should not consider this weight. Okay, this is not a minimum spanning tree. Next, what you can consider means this you can consider. If you are considering this one, this is also not a closed cycle. So how many minimum spanning tree? If you are considering this 0.1, you will be having one minimum spanning tree. If you are considering this one, you will be having one minimum spanning tree, that is second one. If you are considering this edge, you will be having a third one. Okay, and then if you are considering this one, this 0.9 means this will be a closed one. So you should not consider this one. So totally how many minimum weight spanning tree we found it? That is first one. If you are considering this one, that is one minimum spanning tree. And then if you are considering this edge, you will be having a second minimum spanning tree. If you are considering this 0.1, you will be having a third minimum spanning tree. You should not consider this one and this one. Why it is so means, if you are considering this one, it will be a closed cycle. If you are considering this one also, it is a closed cycle. So you should not consider these two edges. You have to consider only this one, this one, this one for forming a minimum spanning tree. So totally how many number of minimum weight spanning tree of the graph we have? Totally 3. This is what the solution for this problem. So once again I am repeating here, minimum spanning tree problem is a repeated one. That is each and every year in GATE exam you will be getting this minimum spanning tree problem. Okay, so you have to concentrate much in this minimum spanning tree problem. Okay, another it is an easy one. Next question number 2. This is also a GATE 2021 question, that is from set 2, previous question from set 1 question paper, right? Here the question is, let G be a connected, undirected, weighted graph. Consider the following two statements. First statement is, there exists a minimum weight H in G which is present in every minimum spanning tree of G. Statement number 2 is, if every edge in G has a distinct weight, then G has a unique minimum spanning tree. So we are going to check which statement is correct, or both these statements are correct, or both these statements are wrong. Okay, so which of the following option is correct? Both S1 and S2 are true. Second one is S1 is true and S2 is false. C option is S1 is false and S2 is true. D option is S1 and S2 are false. So we are going to check which option is correct. Okay, so we are having two statements. First statement is this one. So we are going to check with this one. Statement 1 is that exists a minimum weight H in G. Minimum, I am going to consider this, since it is a minimum spanning tree, we will be considering a minimum that is undirected weighted graph here. Okay, so we are going to consider the undirected weighted graph here. That is, this is, in this we are having 3 vertices and 3 edges. So here there exists a minimum weightage. So I am going to consider the weight 1, 1, 1 here. So in G, which is present in every minimum spanning tree of G. So how to find the minimum spanning tree for this graph actually? What is the minimum spanning tree for this one? This is the minimum spanning tree. So this is not a closed one here. The cycle is not closed here. What is the formula we have? N minus 1. What is N here? N is nothing but 3 here. 3 minus 1 means 2. So how many edges we have? We have 2 edges here. So this is the minimum spanning tree for this graph. Okay, so here that exists a minimum weight H in G which is present in every minimum spanning tree of G. It is not present here. So the statement 1 is wrong here. Next, we are going to check with the statement number 2. What is the statement number 2? If every edge in G has a distinct weight. Distinct weight means what? Different weight with different edges here. So we are considering different weights here. Then G has a unique minimum spanning tree. For this particular graph, what is the minimum spanning tree? This may be the minimum spanning tree here. So here also this condition is satisfied, that is N minus 1. What is N here? N is nothing but 4 vertices, 4 minus 1, that is 3 here. So in this we are having 3 edges. Okay, so here this is the, for this graph, this is the minimum spanning tree. Okay, so in this, if every, what is the statement number 2? If every edge in G has a distinct weight, these are all the distinct weight, distinct means different weights, then G has a unique minimum spanning tree. This is a unique minimum spanning tree. So the statement number 2 is correct. So what is the option number 1? Both S1 and S2 are true. This option is not correct since S1 is false. Second statement is, option is S1 is true and S2 is false. This option is also wrong. What is the option number 3? S1 is false and S2 is true. So this is the correct option for this problem. Okay, this is what the question number 2. Next we are going to see question number 3. This is the question number 3. Let G, this is actually GATE 2020 question. That is, let G is equal to V comma G. Here V is the vertices, G is the edges here. Be a weighted undirected graph, and let T T be a minimum spanning tree of G maintained using adjacency list? Suppose a new weighted edge U comma V belongs to V cross V is added to G. The worst case time complexity of determining if T is still a minimum spanning tree of a resultant graph. This is actually a straight question. So here the option is time complexity is order of mod V. That is option number B. Next one is, this is one interesting problem, that is here this is actually GATE 2018 question, that is consider the following undirected graph, that is this graph we are going to consider undirected graph. Here choose a value X that will maximize the number of minimum weighted spanning tree of G. The value for this one you are going to find it. Okay, so here let us consider, so what is the maximum weight we have here? 4 is the maximum weight we have. So we are going to consider X is that is maximum, sorry, here the maximum weight is 5 here. So we are going to consider 5, 4, 3 and 2. Just a minute. So here number of possible minimum spanning trees increase with non-distinct edges. That is, if we are choosing for that graph, if X is equal to 5 means what is the number of minimum spanning tree for X is equal to 5? Suppose if you are taking X is equal to 5 means what is the minimum spanning tree? What are the possible minimum spanning trees we have? That is, one thing is this one, and then if X is equal to 5 means if you are going to consider, you can consider this one or this one. That is, if you are considering this 4 means how many vertices you have here? 1, 2, 3, 4, 5. Number of vertices is 5 here. What is n minus 1? Here it is 4. How many edges we have now? We have 3. And you are going to consider this 5. Okay, this is one minimum spanning tree if you are taking X is equal to 5. What is the another possibility? Another possibility will be if you are not considering this 4, then you will be having, if you are considering this one, you will be having 2 minimum spanning tree. If you are having X is equal to 4, that is 2 minimum spanning tree you have, and then instead of considering this 5, if you are considering this 5, you will be having 2 minimum spanning tree. So totally how many minimum spanning tree you will be having? Totally you will be having 4 minimum spanning trees if you are taking X is equal to 5. Is it clear? If you are taking X is equal to 5 means for these two 4 you will be having 2 minimum spanning tree, for these two 5s you will be having 2 minimum spanning tree. So totally you will be having 4 minimum spanning tree if you are considering X is equal to 5. Okay, next, if you are taking in that graph X is equal to 5 means, X is equal to 5 means number of minimum spanning tree will be, that is 2 for 2 4s, that is 4 weight edges. Weight is 4 means you are having 2 spanning trees. 1 4 will form the cycle, so you won't be using that 4. That is, if you are considering this 4, you will be having 1 minimum spanning tree. This 4, you will be having 1 minimum spanning tree. If you are considering this 4, that cannot be a minimum spanning tree because this is a closed cycle. Right. So if you are considering X is equal to 5 means you are having 2 minimum spanning tree. Similarly, if you are considering for X is equal to 5, by using 5 you will be having 2 minimum spanning tree. That is this, if you are considering this edge means you will be having 1 minimum spanning tree. If you are considering this edge means you will be having 1 minimum spanning tree. So for 4 you will be having 2 minimum spanning tree. For 5 you will be having 2 minimum spanning tree. So totally you will be having 4 minimum spanning tree if you are considering X is equal to 5. Then then if you are considering in this graph x is equal to 4 means, let us see if you are taking x is equal to 4, what will happen? If you are taking x is equal to 4 here, if you are taking x is equal to 4 means how many minimum spanning tree you will be having here? So what are the things you will be considering here? X is equal to 4 means you cannot consider this 4 because if you are considering this edge means it will be closed. So you will be considering this edge and this edge. X is equal to 4 means that is n is equal to n minus 1 means it is 5 minus 1, that is 4. Here we are having 4 edges here. This is one minimum spanning tree. This is one minimum spanning tree. What is the another one? What is the another minimum spanning tree? You can get it? Another minimum spanning tree will be, you cannot consider this 5. If you are considering this 1 means it will be a closed cycle. So here you are having n minus 1 condition, that is 5 minus 1, it is 4. So you are having 4 edges here. So this is the second minimum spanning tree. So if you are considering x is equal to, if you are taking x is equal to 4 means how many minimum spanning tree you have? Minimum spanning tree is 2. Okay, this is one case. Next one, if you are considering x is equal to 3, x is equal to 3 means what is the minimum spanning tree you can have? X is equal to 3. You cannot consider this 5 because if you are considering this one, it will be a closed cycle. So you cannot consider this one. So if you are considering this one, this is one minimum spanning tree. Okay, what is the another minimum spanning tree? You can use another 2. Another 4 here. Here also the edges are 4 here. So this is the next minimum spanning tree, second one. Okay, so totally in this how many minimum spanning tree? If you are having x is equal to 3, if you are considering x is equal to 3, you are having minimum spanning tree is 2. Okay, that is what I have given here. And then you cannot consider x is equal to 2. There is no weight x is equal to 2 here. Next, we will be considering x is equal to 1. Similar to the previous cases, we can get only 2 minimum spanning tree if the value for x is 1. Therefore, what is the question here? The question is choose a value of x that will maximize the number of minimum spanning tree. That should maximize the number of spanning tree. Which will maximize? If you are taking x is equal to 5 only, it will maximize the count of the minimum spanning tree. Therefore, you are going to take x is equal to 5. If you are taking x is equal to 5, how many spanning tree you are getting? You are getting x is equal to 4. This is what the correct answer. Therefore, your answer for this question is 4. That is the number of minimum spanning tree of G for this value of x. For what value of x? For x is equal to 5, you are getting a maximum number of minimum spanning tree. That is maximum number of minimum. How many minimum spanning tree? That is 4 here for x is equal to 5. Next, we are going to move on to question number 5. This is actually GATE 2017 set 1 question. So in this also we are going to consider one graph, that is with vertices V and edges E, be any connected undirected edge weighted graph. The weights of the edge in E are positive, any distinct values. You are going to consider any positive distinct values in a graph, undirected graph. Consider the following statements. Here the first statement is minimum spanning tree of G is always unique. Second statement is shortest path between any two vertices of G is always unique. So you are going to check which statement is correct, whether one or two or both are correct or both are wrong. So we are going to check which option is correct here. So here what they have asked you to consider it, here you are going to consider the undirected graph with edge values are positive and distinct values. So here I am going to consider this graph. That is, here I am considering 4 vertices with 4 edges with distinct values. What is the minimum spanning tree for this problem? This graph, this is the minimum spanning tree. So what is the first option we have? Minimum spanning tree of G is always unique. So this is actually a unique. So the first statement is correct. What is the second statement we have? Shortest path between any two vertices of G is always unique. This is what we are going to check next. That is the second option. So here what is the condition they have given? It should be a undirected graph with edges, positive values and distinct values. So I am going to consider this graph here with vertices A, B, C with edge weights 1, 2, 3. What is the path, shortest path for this particular graph? So this is the shortest, that is to reach A to C. What are the shortest path we have? That is straight away you can reach. So if you are reaching straight away means your shortest path will be 3 here. What is the another way we can reach it? We can reach C via B also. In this we are having A to B, B to C. That is 1 plus 2, 3. So here this thing, that is shortest path between any two vertices of G is always unique they have given. It is not correct. It is not unique actually. Therefore, second option is wrong. So, what is the correct option for this problem? This one. That is, it will have minimum spanning tree of G is always unique if you are considering the edge values positive and distinct values if you are considering means this is the correct option. So first of all you have to be careful, very careful while reading the problem. First you have to check what are all the conditions, you have to note down what are all the conditions they have given. Based upon that you have to consider the example, then only you will get the correct answer. So in this they have given distinct values. So if you are considering a same values you will not get the correct answer here. So you have to read the question properly and then you have to solve the problem. Next we are going to see question number 6, that is this comes in GATE 2016 set 1 question paper. Here what they have considered in the problem means let G be a weighted connected undirected graph with a distinct positive. Here also in this problem also we are going to consider distinct positive edge weights. That is weight should be a different values here. If every edge weight is increased by the same value, then which of the following statement is true? That is the two statements they have given. First statement is minimum spanning tree of G does not change. Minimum spanning tree does not. First option they are talking about the minimum spanning tree. Next thing is shortest path. First one is minimum spanning tree. Second option is shortest path between any pair of vertices does not change. We are going to check whether these two conditions are true or one condition is true or both are wrong. Okay. First, for checking with the first option, this option, we are going to consider one graph, that is undirected graph with distinct positive edge weights. So this is what the graph one, this is for point option 1 we are going to check it. That is with the distinct edges we have. This is what here in this graph we have 4 vertices. So here for this particular graph, what is the minimum spanning tree? this will be the minimum spanning tree. That is, what is the condition we have? That is n minus 1. What is n minus 1? Here 4 vertices we have, 4 minus 1 is 3. So here we are having 3 edges. Therefore, this is the minimum spanning tree for this particular undirected graph. So here 1, 2, 3. This is what the actual minimum spanning tree for this particular graph. What is the condition they have given in the problem? If every edge weight is increased by the same value. Every edge weight, this is actually the edge weight. If this each edge weight is increased by the, note down here, the same value, then which of the following statement is true? That is first statement, minimum spanning tree of G does not change is the first condition. So each edge weight is increased by some value, that is all the edges should be added with the same value. It should not be at different values. Okay, so if you are changing like this, what is the value you will be getting in the minimum spanning tree? 11, 12, 13. If you are adding some value to that edge, whether this minimum spanning tree is changing, it doesn't change. Therefore, this condition is true. So first we are going to check with the statement number 1. What is the statement number 1? We are going to check with the minimum spanning tree of G does not change. So here first thing is consider one graph. This is one graph. So here vertices, you are going to consider distinct positive edge weights. Values are distinct and positive weights here. So for this particular graph, what is the minimum spanning tree? This is actually the minimum spanning tree. So what is the condition for the minimum spanning tree? N minus 1. What is n minus 1? Here number of vertices is 4, minus 1, that is 3. In the minimum spanning tree, we are having 3 edges here. Therefore, this is the minimum spanning tree for this particular graph. What is the second condition they have given? Every edge weight is increased by the same value. You are going to increase the edges with the same value. I am going to increase the edge weight with 10 here. Okay, I am increasing with 10 value means what you will be getting here in the minimum spanning tree? Here 11, here 12, here 13. So whether in the minimum spanning tree, whether the minimum spanning tree is changing here, it doesn't change. Therefore, the statement number 1 is correct here. What is the statement number 2? Shortest path between any pair of vertices does not change. What is the second? This is the second option. That is, we are going to talk about the shortest path between any pair of vertices. Shortest path means I am going to consider this graph, that is with vertices, with 4 vertices and 5 edges with weights 1, 2, 3, 4, 5. So I am going to find the shortest path for V1 to V2. So if you want to reach this V1 to V2 means how we are going to reach? The first thing is this one, that is V1 to V2 means 1 via this one and this one, 1 plus 2, that is 3. This is one path. Another path is straight away you can reach, that is 5, and another one is how you can reach here, this one via here also, V1 to V2 you can reach, that is 4 plus 3 is equal to 7. So here what are the ways we can reach V1 to V2? Shortest paths are 3, 5, 7. The shortest path is 3. This is what the actual problem. The next, what they have given the condition, if every edge weight is increased by the same value. Now I am going to add as usual some value here with the same value. That is what the condition they have given. I am going to add the same value 50 throughout the edges here. So if you are adding like this, what is the shortest path you will be getting to reach this V1 to V2? What is the first step we can do it? This is 51. 51 plus 52, 103 is one thing. Here itself it is done. Shortest path is not same here. Therefore, shortest path between any pair of vertices they have given does not change. It will change here. Shortest path will be changed if the weight is increased by some value. Okay. Therefore, second statement is wrong. Therefore, what is the answer for this particular problem? Option A is your answer. This belongs to GATE 2016 set 1 question. So once again I am repeating here, minimum spanning tree is one of the important topic in GATE exam. That is, each and every year you will be getting at least one problem from this minimum spanning tree. Next, question number 7. This from GATE 2016 set 1. Okay, so here let G be a complete undirected graph on 4 vertices. Here they have given what is the weight, that is edge with weights they have given. Okay, we cannot consider by our own. So here having 6 edges we are going to consider with the weights 1, 2, 3, 4, 5, 6. Maximum possible, we are going to find what we are going to find. It means the maximum possible weight that a minimum weight spanning tree of G can have is, that is maximum possible weight that a minimum weight spanning tree, that is, first you are going to find what is minimum spanning tree for this particular graph, and then we are going to find what is the maximum possible weight for that particular minimum spanning tree. So here they have given it should contain 4 vertices, undirected graph with 4 vertices. So here undirected graph with 4 vertices, and it should have a 6 edges, 1, 2, 3, 4, 5, 6 edges we have, and with values 1, 2, 3, 4, 5, 6. So 1, 2, 3, for this edge I have taken 4 weight, this one is 5, this one is 6. So I am going to find the minimum spanning tree for this one. Okay, so this is what the minimum spanning tree, because if you are considering this edge means that will be a closed one. So we cannot consider that one. If you are considering this lowest also, this is a closed one. If you are considering this one, this is also a closed cycle. Therefore, this is what the minimum spanning tree for this particular graph. So what is the condition? Should be satisfied, n minus 1. What is the n here? N is the number of vertices. Number of vertices is 4. 4 minus 1 is 3. Therefore, you have 3 edges here. Therefore, this is a minimum spanning tree for this particular graph. Why we are not considering this edge? If you are considering this edge means it will be a closed one. If you are considering this edge also, it is a closed one. If you are considering this also, it is a closed one. So only possible minimum spanning tree for this graph is this one. They have asked you to find what is the maximum possible weight that a minimum weight spanning tree. So this is a minimum spanning tree. So you are going to find the maximum possible weight. What is the maximum possible weight now? 1 plus 2 plus 4 is equal to 7. So the answer for this one is 7. We will move on to question number 8. That is, this question we have seen in GATE 2015 set question number set 1. That is a graph shown below 8 edges. That is in the next slide I have given. That is with 8 edges, with a distinct integer edge weights. Here also distinct weights we are going to consider in this graph. Minimum spanning tree is of weight 36 and contains the edges. These are all the edges they have given in the problem. So based upon this, we are going to draw the undirected graph with 8 edges. The edge weight of only those edges which are in the minimum spanning tree are given in the figure shown below. The minimum possible sum of weights of all edges of this graph. So you are going to consider minimum possible sum of weights of all edges, 8 edges of this graph. That is, only these edge values for these things they have given. We have to take the values. We are going to consider some values for these edges. edges, that is A to C, B to C, B to E, E to F and D to F. Okay, so example, we will consider this graph. Here we are having 8 edges. So here we are going to consider, that is A to B. For A to B they didn't give the value. For A to C they have given the value. You can consider A to C and then B to C, B to E, E to D they didn't give, C to D they didn't give, E to F and D to F. These are all the values we are going to consider. We don't know the value for these 3 edges here. So next thing is we are going to come into the solution, that is we are going to find what is the minimum possible sum of weights of all edges, 8 edges of this graph, that is weight is they have given 36. So we will solve, we are going to see how we are going to solve and get the solution for this problem. Okay. Now the solution for this problem is, this is actually a graph what we have seen in the previous slide. So we have given the weight for the vertices what they have given, that is edges what they have given here. So A to B we don't know what is C to D and we don't know what is E to D. So we are going to find the maximum, that is total sum of the edge weights here. So we don't know this one and this one. Okay, we are going to find what it is here. So here in ABC, that is first consider this part alone, that is in ABC, AC and BC are the part of minimum spanning tree, that is for this graph alone. What is the minimum spanning tree? This will be the minimum spanning tree, that is 2. This will be the minimum spanning tree, or otherwise what will be the minimum spanning tree here? This can be the minimum spanning tree. So what we can have for this value, what is the condition they have given in the problem? AB is not included, included means AB should be greater than the maximum of AC comma BC. That is, you have to consider the maximum of this two, that is maximum of BC comma AC, that is maximum of 2,9. What is the maximum of 2,9? That is 9. What is, you have to take only greater than that value. What is the greater than this value? You can take it 10 here. So you can consider here 10 here. Okay. You got one edge value, that is A to B. Next we are going to find the edge value CD here. So similarly, minimum value is AB is equal to 10 we have taken. Similarly, you consider then DEF, that is you consider this graph. Okay, for this graph, what is the minimum spanning tree you can take it? Minimum spanning tree will be E, F, D, that is 4, 6. What is the maximum value among this? Maximum value is 6 here. So what you can take it for this one? Greater than this maximum value. Greater than this maximum value means you can take it as 7 here. So this value will be 7 here. So you got the edge value for D to E here. Next, the only one value left out here is CD. So for this you are going to consider the graph B, C, D, E. Okay, if you are considering B, C, D, E in this 3 vertices, by using these 3 values you can find this one. What is the maximum value? Maximum among these 3 values, this one and this one. This is the maximum value. So you can take the greater than this maximum value. What is the greater than this maximum value? That is 16. So what you got it? Here 16. So already they have given in the problem the weight for the remaining edges are 36. What we got for the remaining is 10 plus 7 plus 16, that is 33. So total weight for the problem is 33 plus 36. 33 plus 36 is 69. Therefore, your solution for this problem is 69. Once again, I'm repeating here, that is, you don't know the weights for this one and this one. So first you consider A, B, C alone. For that you find the minimum spanning tree. Maximum value among these two 9 and 2 edge weights are 9 is the maximum value. Greater than that 9 is 10. So you are taking A to B is 10. Similarly, you consider this graph and then this graph. So you got 7 and 16. So totally you have what we have find 3 edge weights we have found, that is 10, 16 and 7. So you just add those 3 values and what they have given for the remaining weights, that is 36 they have given, that is what we have splitted in this graph. So 33 plus 36 is 69. So maximum weight for this problem is 69. Clear? This is what the graph we have considered. So greater than this 9 value is 10 we have taken, and then we are considering this graph alone. For this, the maximum value is 6. Greater than 6 is greater than 7 is greater than 6. So we are considering here 7 here. Next we are going to consider this part. In this, the maximum value is 15. So 16 is greater than 15. So we are taking 16 here. So what we found, the remaining values they have given in the problem is 36, and 10 plus 16 plus 7 is 33. So totally 36 plus 33 is 69. This is what the required answer for your problem. I think it is clear to everyone. So the answer for this one is 36. Is it clear to? I think it is clear. So with this, I will stop my lecture. There is 8 questions we have seen in this minimum spanning tree. In the next video, I will be doing the remaining problems in a minimum spanning tree. Thank you. Thank you everyone.